What is gravity? Oh, well, that's pretty easy. Isn't it like that thing that makes you fall? Well, yeah, pretty much, but what really is gravity? Well, in the 1600s, Isaac Newton described it as a pulling force that all objects exert. That means everything in the universe is pulling on you. Well, in that case, how are you even still on Earth? Well, to find out, let's look at Newton's gravitational equation, which is F equals G times m1 times m2 divided by r squared. F is the force of gravity. G is the gravitational constant, which is a very, very small number with a lot of units attached to it. M1 and M2 are the first and second masses of the two bodies of mass that we're doing the calculation for. R squared is the distance between these two bodies of mass squared. The fact that the distance is squared in this equation means that the force due to gravity grows exponentially the closer you are to an object, and inversely weakens exponentially the farther away you are. This is why even though the Sun has 333,000 times the mass of Earth, its gravitational pull on us is only about 0.06% that of the Earth's. This is because the Sun is 149.6 million kilometers away, whereas the Earth is a bit closer to us than that. Although this view of gravity works well enough, Einstein had a different idea. In his theory of special relativity, Einstein stated that gravity isn't a force at all, but rather a curvature in space-time. So what does that mean? Well, we can explain this a bit better with a
do-it-yourself experiment.
So for this experiment, what you're going to need is a flexible sheet, a heavy ball, and a lighter ball, like a golf ball. If we roll the lighter ball across the sheet, you'll notice that it'll travel fairly straight until it reaches the end and starts to roll back. Now if we add the heavier ball to the center of our sheet, the sheet around the ball will start to curve, with the ball being the center of it. Now if we roll the lighter ball, it'll start off going straight, but then curve due to the sheet's curvature, and then end up hitting the heavier ball. This sheet is space-time, and the heavier ball is curving the space-time. So even though the lighter ball is trying to just go straight, it starts curving towards the heavier ball. This is how Einstein thought of gravity. But this two-dimensional model can't possibly work for a at least three-dimensional universe. What about the area underneath the sheet? How will objects under there curve towards the heavier ball? This model doesn't account for that. Well, to envision an at least three-dimensional space-time, let's take that sheet but make it 3D. Let's also make it hollow so that we can see better. There. Now if a body of mass were to appear at the center of our space-time, then the space-time around it will start to curve inward towards it like this, with the mass of the body dictating how much it'll curve. Though this is the perfectly accurate representation of what a three-dimensional space-time would look like, it does account for many of the issues that we had with the previous two-dimensional model. Gravity doesn't just distort space, though. It distorts space-time. This may be why gravity has a rather interesting effect on our perception of time. It's well known that areas with more intense gravity experience slower time, and vice versa. For example, an Earth day on the Earth is 86,400 seconds, but an Earth day on the Sun is 86,400.2 seconds. This means that if you were to stay on the Sun for 432,000 years, then you would most certainly be dead, but if you weren't, then you would actually be a year younger than if you had stayed on the Earth. How? Well, the Earth still revolved around the Sun 432,001 times, but due to the Sun's stronger gravitational pull on you, only 432,000 years would have passed for you. This is because time is relative to whatever is experiencing it, and it doesn't pass at the same rate for everything, which makes it rather difficult to measure universally. In the previous example, what if you on the Sun said that 432,000 years had passed, but Jeff on the Earth said that 432,001 years had passed? Who would be right? Well, Jeff would be right. Why? Because the technical definition of a year is the amount of time it takes for the Earth to revolve around the Sun. This means that a reference point for time is the Earth, and from the Earth's perspective, Jeff would be right. So, why does any of this matter? Well, in your normal day-to-day life, it doesn't really, but sometimes it's nice to think beyond that and really be fascinated by all the odd ways in which the universe functions.